we start chapter 3 memorizing our perfect squares. The reason why we're going to memorize our perfect squares is because the first thing we're going to do in this chapter is learn how to simplify radicals. What is the square root of 200? I don't know. But I do know that it simplifies to 10 times the square root of 2. And you will need to be able to do things like what I just did. First 20 perfect squares, you need to memorize them. So I take the number 1, I square it. That means take a number and multiply it to itself. 1 times 1 is 1. That one's easy. 2 squared. That means 2 times itself. 2 times 2. 4. 3 squared means 3 times itself. 3 times 3 is 9. You see, 9 is the perfect square. 3 is the root, the square root. Okay, we got to have our vocabulary straight also. 4 squared, 16. 5 squared, 25. 6 squared, 36. 7 squared is 49. 8 squared, 64. 9 squared is 81. 10 squared, easy, a hundo. Now, obviously, 1 squared is 1. That one's not really super important because it's never going to matter. But the other ones, the other 9, 2 through 10 squared, are imperative. You either know those or just take an L, okay? Just know those. Now, you want to know the next 5. You really, really want to know. You need to know the next 5. 11 squared, 121. 12 squared, 144. 13 squared, 169. 14 squared, 196. And then 15 squared, 225. So the first 10 perfect squares, imperative, absolute must. Next 5 perfect squares, 11 through 15, yeah, you really kind of need to know those. You need to. So must, 1 through 10. Need, 11 through 15. Want, 16 through 20. (16 squared) 2, 5, 6. 17 squared? 2, 8, 9. 18 squared? 3, 2, 4. 19 squared? 361? That's the only one that I struggle to remember sometimes. Pretty sure it's 361. And 20 squared is 400. And let me grab a calculator real quick just to make sure 19 squared is 361. It is. Okay, just making sure. Double checking. That's the only one I question myself on. I don't know why. But for some reason, 361 just doesn't jump out to me. Interestingly enough, it begins with a perfect square, 36, and ends with a perfect square, 1. Neat. There you go. The first 20 perfect squares. Not only do you want to know these numbers, you also need to know some multiplication tables. You want to know some multiples of these numbers. You want to know what 16 times 2 is, 16 times 3 is, 16 times 4, and 16 times 5 are. You want to know these things. You want to know what 25 times 2, 3, 4, and 5 is. You want to know what 49 times 2 and 49 times 3 is. You want to know these things. And if you don't know them, well, I mean, yeah, you could still succeed, but it'll be much, much faster if you do know them. It's like when someone asks me for more time on a test and I've watched them stare at the same 5 questions blankly for 30 minutes ago, I need more time. Why? The only reason why you're not finishing is because you don't know what you're doing, not because you need more time. You see, going home and studying more is cheating. So if you know these things, you won't struggle for time, I promise you. Let's go ahead and reset the slide, and we are now going to use these first 20 perfect squares. We're going to write these roots, these radicals, in simplest form. That doesn't mean grab a calculator and try to figure out what the square root of 20 is. I mean, I don't know what the square root of 20 is. I know it's somewhere between 4 and 5, but that's not what I'm asking you to do. I'm asking you to simplify it. How do we do that? Well, the Algebra 1 way to do it. Let me show you what you did in Algebra 1. You took the 20 and you split it into 2 times 10. And then you took your 10 and you split it into 2 times 5. Will this method work? Yes. But what if the numbers are gigantic? You're going to be working for quite a while. I don't want you doing this. If you need to, fine, whatever. But I'm telling you, you don't want to do it this way. Instead, what you want to know is you want to know what perfect square could you divide the number 20 by without getting a decimal. So you look at your list of numbers, the perfect squares, and you ask yourself, and by look, I mean up here in your head, and you ask yourself, which perfect square can I divide 20 by? It's very simple. 4, not 2. 2 is its square root. We're talking the perfect square. We can divide 20 by 4. So what you're going to do is you're going to call 20 4 times 5. The first number is a perfect square. The next number, the 5, is not. And not only is 5 not a perfect square, I can't divide it by any perfect squares other than 1, and that does me no good. 1 goes into everything, so we're never going to use the number 1 when we're reducing our radicals. So I've split it into 4 times 5. Again, I chose 4 because it's the biggest perfect square that I could divide 20 by. I can now take the square root of 4 out of the radical. The square root of 4 is 2. But the 5 is stuck because I can't do anything with it. That is the square root of 20 written in simplest form. It is 2 times the square root of 5. We are fascinated with our water bottle this morning, aren't we? Trying to be active participants in our education. Okay. 50. The Algebra 1 way of doing it. Oh, by the way, if you were trying to do the Algebra 1 way, square roots are looking for pairs of numbers. So you would have taken this 2 2's and written it 1 time on the outside, which works when numbers are small. It's not hard when numbers are small. But when numbers are big, like, I don't know, the square root of 441, the last thing you want to do is start splitting that apart into tiny numbers. It'd be better if you knew that the square root of 441 was 21, So 50, the Algebra 1 method. 2 times 25, and 25 is 5 times 5, and we're going to hunt for pairs of numbers. The Algebra 2 method, the educated way of doing it, is to ask yourself, what's the biggest perfect square I can divide 50 by? 25. And you ask yourself, how many times does 25 go in? It goes in twice. See, the first number is a perfect square, and the last number is not. And I can't simplify that last number. It's just a 2. So the square root of 25 comes out. It's 5. But I can't do anything with the 2, so it's stuck. Just like that. Again, the Algebra 1 method would have been like, okay, 2 times 25. Oh, and the 25 is 5 times 5. And oh, look, here's a pair of 5s. I'll take the 5s out, and I'll leave the 2 inside. It's the same answer, but it's more work. $48. 48's a special number. It comes up a lot. I don't know why. Honestly, I don't know why. But it comes up a lot. Algebra 1. 2 times 24. 2 times 12. 2 times 6. Oh no. 2 times 3. Look how much work I had to do. No, no, I'm not trying to do all that crap and then hunt for pairs and no, 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 no. No, 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 no. Instead, what I'd like you to do is tell me the biggest perfect square that you could divide 48 by. 16. 24 is not a perfect square. Look at your list of perfect squares. You will see that 24 is not on there. But 16 is. You see, 48 is 16 times 3. Mr. M, I'm never going to memorize things. I just can't. I smoked away my memory. Can I have another option? Sure. I think it's obvious that you can divide 48 by 4, right? So let's just say you did it that way. So 4 goes in 12 times. If you need to, you could then ask yourself, could I divide 12 by a perfect square? Yes. You could divide 12 by 4 again. Again, this is more work than I want you to have to do. And pairs of things get to come out. But that's too much work. It's too much work. It would just be great if you knew that 48 was 16 times 3, because the square root of 16 comes out, and the 3 is stuck. Now down here, you go, okay, I see a pair of 4s, so the pair of 4s gets to come out as one number, and it's just 4 root 3. I mean, look, it's the same answer, but it was more work. We're trying to avoid more work. Yes, sir. Yeah. Trying to avoid more work. You like doing more work? Fine, go for it. I'm fine with that. You want to make a factor tree every time I ask you to do one of these? Shoot, go for it. I just don't want to hear anybody complain about time come test day. Because I'm going to say, wow, you haven't memorized your perfect squares yet? What are you doing? Okay, 45 can only be divided by a single perfect square. Those that know our times tables instantly know what perfect square goes into 45.
Is it 9 and 5?
It is 9. 9 is the perfect square that goes into 45. And it goes in exactly 5 times. And then the square root of 9 gets to come out. The square root of 9 is 3. Because 3 times 3 is 9. Done. 3 root 5. I don't know what that number is. I know it's a little bit less than 7. I know that. But I don't know exactly what it is. It's 6 and change. It's probably like 6.8 or something like that. Ish. And then lastly, for this slide at least, 72. Now 72 is one of those numbers that more than one perfect square can go into it, like 48. You're trying to do as little work as possible though, right? I mean, we are high school students, right? We're trying to do as little work as possible. So your job is to figure out the biggest perfect square that you can divide 72 by. It is 36. 36 goes into 72 twice. Mr. M, there was no way I was ever going to pull 36 out of a hat. Fine. Hopefully you know that 9 goes into 72. And then 4 goes into 72. So if you have to split it into more perfect squares that are smaller, fine, whatever. I'm just trying to save you some work. The square root of 36 gets to come out. It is 6. The 2 is stuck. We good? Yeah? Okay. A word on square root bars, square root symbols. I can't tell you the number of times over the last, this is now my 6th year teaching this course, and every year I've taught at least 2 classes of it, so you're like the 14th or 15th round of students that I've had come through this Algebra 2 classroom. And I can't tell you the number of times that I have seen someone say that the square root of 9, for example, is the square root of 3. This is not true. You see, the square root of 9 is 3, not square root 3. That is what you're supposed to do. So what's the difference? What are those students doing wrong? those students are keeping a square root bar after it has done its job. A square root bar is like firecracker. It's one and done. Gone. If it gets to do its job, it's gone. If it can't do its job, it's stuck. Kind of like here. You see, it couldn't do its job on this number. And that's why that number was stuck with the symbol square root bar. It was able to do its job on the 36. That's why there's no radical on the 6 at the end, because it was able to do its job. So when it does its job, the symbol is gone. For example, 4 plus 1 is 5. You see how I didn't say 5 plus? Why? Because the symbol was able to do its job, so I didn't say it anymore. How about this? X plus 1. You know what that is? It's x plus 1. You see, the plus sign couldn't do its job because those aren't like terms, so I was forced to say it again. When a math symbol gets to do its job, the symbol is one and done and gone. And that will always be true. If a symbol can't do its job, that symbol hangs around, okay? Just putting that out there because I can't tell you the number of times that I have seen that square root bar stick around. I can't tell you the number of times I've had students tell me that the square root of 16 was the square root of 4, which is 2. No, absolutely false. You see, 16 is a perfect square. The square root of 16 is 4. The symbol was able to do its job, so finished. Symbol gone. Yes, sir.
For the very first one, the square root of 20, why did you do 4 times 5 instead of like 2 times 10?
Because 2 is not a perfect square, and 10 is not a perfect square. You see, when I'm splitting my numbers, when I'm splitting my biggest number, I'm splitting it so that one of those is a perfect square that the symbol can do its job on. So is 22 times 10? Yes, it is. But unfortunately, the square root of 2 can't do a job. Square root of 10 can't do a job. So I would be forced to then split the 10 into 2 and a 5. And now you're doing the whole factor tree, and I don't want you to have to do that. So we're specifically saying, what perfect square can I divide by? Can I divide by 4, 9, 16, 25, 36, 49, so on and so forth? So the ones that I wrote in on the very first slide, those are the ones you're asking yourself, can I divide by one of these? That's what you're hunting for. Okay? That's a great question. So do we understand what I was getting at over here with these red and green circles? Once a symbol gets to do its job, it does its job one time and then it's gone. Square root of 16 is 4, not the square root of 4, which then turns into 2. Doesn't work that way, okay? All right, cool. Can I move on, or are there more questions? Because that was a really good question. Are we good? No one's going to freak? Everybody at home? You guys straight? Okay. Boink. Just waiting on the panel. Oh, there we go. Okay, cool. Let's step up our game. Eek, fractions. Oh my God, so scared. Well, no big deal. You know why it's no big deal? It's no big deal because the square root of a fraction is the same thing as saying the square root of the top and the square root of the bottom. That's all it is. It's not the end of the world. Square root of 4/9 is saying the square root of 4 divided by the square root of 9. Okay, well, 4 is a perfect square. Its square root is 2. Symbol gone because it got to do its job. And hey, 9 is a perfect square. Square root of 9 is 3. Symbol did its job, so it's gone. We're finished. There you go. The square root of 4/9 is 2/3. Very simple. Now, my strong suggestion would be to simplify your fractions if you can before you bother doing any square root stuff. So this next one, 12 over 50, it reduces. So because the fraction reduces, you should reduce it first. Just go for it. Reduce it first. Is it always necessary? No, but you won't go wrong doing it. So let's see. What can I divide 12 and 50 by? 2. Yeah, I can divide them both by 2. So if I divide both these numbers by 2, what I get is 6 over 25. And well, looky there. 25 is a perfect square. That means the square root bar can do its job on the bottom of this fraction. That makes us happy. Mathematicians don't like square root bars in the bottoms of fractions. It's a big fat no-no until you get it up into super high mathematics where it's just easier to do the math when there is a square root down there. We just don't let it happen. Now, 6. 6 cannot be divided by any perfect squares. 6 is literally just the numbers 2 times 3. And since neither one of those is a perfect square, there is no reason to split the number 6. That means the symbol is stuck on the 6. It can't do anything. But the square root of 25 is just 5. There, symbol did its job. Boom, done. Yes, sir. Right? If you didn't reduce it, it wouldn't be a completely different answer if you kept simplifying. So what happens if I don't reduce it? Square root 12 over square root 50, right? So what happens if I don't reduce? What perfect square goes into 12? 4. So I could split 12 into 4 times 3. And what perfect square goes into 25? Or crap, I said it. Into 50? 25. I hate when that happens. Teachers do that junk all the time. Like this. Okay, so square root of 4 is 2. The root 3 is stuck. Square root of 25 is 5. The root 2 is stuck. And I'm telling you that these two answers are identical to one another. Now here's why. Remember a second ago I just told you mathematicians do not like radicals in the bottom? They're not allowed. So what you would have to do is something that we call rationalizing the denominator. Gee, that sounds special. I wonder if Mr. M was hoping someone would ask. I wonder if it might end up as an extra credit question sometime in the future. This is how you rationalize the denominator. It's called rationalizing the denominator because the number square root 2 is irrational, meaning there's no way to represent it without rounding our decimals. This is the best way to write it. Here's how you would fix this thing so that it did not have a square root in the bottom. You know how you're allowed to multiply fractions by the same number on the top and bottom? Like, you know how 1/2 is the same as 4 over 8? Like when you're looking for least common denominators and stuff? I'm going to multiply the top and bottom by the thing that's not allowed. And here's why. This will give me 2 times the square root of 3 times 2. See, I put the root 3 and the root 2 together. And on the bottom, this will give me 5 times the square root of 2 times 2. But the square root of 2 times the square root of 2, that's the square root of 4, right? What's the square root of 4? It's 2. So what this gives me is a 5 times 2 on the bottom and a 2 times root 6 on the top. And then watch this. Root 6 over 5. You see, it is the same answer. It just takes more work to get there. Right. No radicals allowed in the denominator. And if it happens, you must rationalize the denominator by multiplying the top and the bottom by whatever that no thing was. And the square root 2 was not allowed down there. Like, for example, if I had a square root 5 down there, not allowed. Multiply the top and the bottom by square root 5. And I don't know if you guys caught this, but the trick was when I multiplied a radical to itself, the result was that number written one time. So root 2 times root 2, 2. Root 3 times root 3, 3. Root 5 times root 5, 5. Lewis, you're still processing something. Wow, what's up? No, it was 5 times 2. Because right here I had a multiplication dot, and rather than actually multiply them, I saw that, oh, the 2's are going to cancel each other, so I'll just go ahead and cancel them. You could, but then you'd have to reduce the 2 over 10 to 1/5. So again, I was just trying to save you a step. So could you call it 2 root 6 over 10? Sure, but you're not finished until you reduce the 2 over 10 to a 1 over 5. So I was just trying to save you the work. Look how much more work it is to get to the same answer, you know? But it shows a really good process. I'm glad you asked. Now, let me tell you what you're not allowed to do on this next one. You're not allowed to reduce the fraction. You can't reduce this fraction. The way it sits right now, that's not possible. You see, because the 18 is inside a radical. Are you even, like, with me right now? What are you smoking over there? Come on. Pay attention. You two should not sit next to each other. Terrible for your education. In case mom's ever watching, Graydon should not sit next to his buddy Kevin. All right, so this 18 is inside a radical. This 6 is not. Because the 18 is inside the radical, it cannot work with the 6 that's outside. It's kind of like transformations where I said inside things can never change outside things. It's the same idea with radicals. Inside stuff cannot work with outside stuff. So what do? Your only option is to reduce the radical that you have. Your only option is to tell me what perfect square. That's red. I don't like it. There we go. Your only option is to tell me what's the biggest and only perfect square that goes into 18. 9. 9 goes in twice. Now the square root bar can do its job. Yes, sir, Sam. What's up?
What if you made the 6 the square root of 36 and then reduce that?
You could, Sam. Okay, so I don't know. Did you guys at home hear what he said? No? Catherine shook her head no. Sam asked me, could I call 6 the square root of 36 and then reduce that way? Yes, you could. But it's going to require you to be able to rationalize the denominator in a minute. So that's the only reason why I'm not going to do that. But you could. It'll get you there, but it's not worth the amount of effort you would have to put into it. But it works. I mean, that's a you know, no one's ever asked me that before? But yeah, you can absolutely do that. I wouldn't, but you could. Wow, no one's ever asked me that. So interesting. You think you hear all the questions, but you've never heard all the questions. That one was a good one. Square root of 9 gets to come out. Square root of 9 is 3. The 2 is stuck. And like Lewis and I were talking a moment ago with that 5 times 2 on the bottom, I would have ended up with a 2 root 6 over 10, which I had to reduce. This reduces. This 3 and this 6 can both be divided by the same number. I can reduce this fraction because these are both outside numbers. They can both be divided by 3. So it's going to give me a 1 times root 2 on the top and just a 2 on the bottom. Now, Sam, if at the very beginning I had called 36 the square root, if I had called 6 the square root of 36, which I would have ended up with the square root of 18 over 36, which is 1/2, right? So it's the square root of 1/2, which means square root of 1 over square root of 2. That's just 1 over the square root of 2. Then you would have to go through the whole rationalizing denominator process. But it is the same answer. So this number, square root of 2 divided by 2, is the same as 1 divided by square root 2. But you would have to rationalize the denominator, so I'm trying to save you those woes. Okay. If you ever decide to take trigonometry and things like that, trigonometry is where the teachers will sometimes start to say, you know what, don't bother rationalizing denominator. It's too much work for me to figure out what your answer was. If you rationalize the denominator, just leave it. 1 over root 2 would be perfect. In fact, I teach pre-calc and trig more than to one. I teach it to the pre-calc kids and to the IB kids, and I tell them, leave it 1 over root 2. Because that makes my life easier. But in this course, you're not allowed to. So problem solving strategies. Oh, that's good. Okay, so I've started to get a little ridiculous here. Radicals in the top and bottom. Negatives. Oh no! Whatever will I do without my calculator? You will suck it up. That's what you'll do. Deal with it. Now on the top, I can't do anything. It's already square root 2. It's stuck. My only option, work with that number 128. Wow, that's kind of a big number, and it's not a perfect square. But I can divide it by a big perfect square. 64 goes into it. How many times? 2 times. Mr. M, I was never going to see that. How would I have known? Okay, well, I mean, You could have split it into 4 times 32, and then 32 is 4 times 8, and 8 is 4 times 2. You could have done it that way. It's a lot more work. I don't want you to have to work with factor trees, but if you have to, you do it, okay? But I would love for you to know a couple multiples of your perfect squares. Know a few of them. Know what each of those numbers times 2 and times 3 is. I'm not going to give you gigantic numbers, so if you know what they are times 2 and times 3, you're pretty much set. I'm going to be real with you. I think the next test is no calculator. So you better know how to multiply and divide. So, okay, well, the square root of 64 gets to come out. It's 8. And, oh, crud, I can't do anything with that root 2. But any number divided by itself is 1. So root 2 over root 2 just cancels out, leaving me with negative 4 over 8, which reduces, divided both by 4. Negative 1/2. Wow. Do you have any idea at the very beginning that the answer was going to be negative 1/2? That all that other junk just simplified away? So cool. And the last one on this slide. Oh boy. Well, 90 is not a perfect square. Neither is 40. But they can both be split. What is the only perfect square that goes into 90? It's 9. It's 9. It's actually 9 times 10. And there's more than one perfect square that goes into... No, there's only one perfect square that goes into 40 as well. Come on, guys. It should be obvious to more than just Lewis. 4. So here's the question. On the top, I could take the square root of 9 out. What does that mean? There's already a number there. Well, the number negative 8 is actually saying times whatever this thing is. So when things come out, the multiplication dot still exists. The square root of that 9 comes out, and the 10 is stuck. Could I multiply those two numbers right now? Yes, I could. But I'm going to wait. I'm going to wait and hope that something really easy pops out of the bottom that I could just cancel away immediately. Let's see. Square root of 4 comes out as a 2. Oh, and then the 10s are stuck. Oh, well, you know, it didn't really work out all that well. That's okay. It was still worth hoping for. So on top is negative 24. Again, no calculator. You need to know how to multiply and divide. The bottom is 2. And negative 24 divided by 2 is negative 12. So all of this mess equals negative 12. You guys got any questions for me? No? Okay. And then I'll clear it. It's time to pop some brains. Here we go. You guys ever seen Alice in Wonderland?
Yeah.
We're about to dive down the rabbit hole. Definition of a perfect square is a number that is found by multiplying a number to itself. For example, 9 is a perfect square because 3 times 3 is 9. 16 is a perfect square because 4 times 4 is 16. 36 is a perfect square because 6 times 6 is 36. I would like you all to look at the 20 perfect squares that we wrote at the beginning and tell me one thing they all have in common. Something insanely obvious, so obvious you might not even realized it. Oh, okay, Lewis realized it. They're all positive. Because anytime you multiply a number to itself, you get a positive result. Positive times positive, positive. Negative times negative, positive. So here I have the square root of negative 1. There is no number that when you multiply it to itself, you get a negative result. So
would it be I?
she has seen some things before, but yes, Catherine's absolutely right. The square root of -1 is known as the imaginary unit I. By definition, the square root of -1 is equal to I, where I represents the imaginary unit. Your number line is where all of the real numbers exist. I could write them on a number line, correct? Left to right. You have it in your mind then that numbers are one-dimensional. A straight line is one-dimensional. Wrong. Numbers have two dimensions. They have a real component and an imaginary component. Now, all real numbers have 0 imaginary components to them. But every number can be written as a two-dimensional. Do you need to know that for this course? No, but that's what this means. By definition, the square root of any negative number is imaginary, quote unquote. That doesn't mean we made them up. It's an unfortunate name. Okay. So what do we do? Well, anytime you see a negative sign inside a radical, you could just pull the I to the outside, and now you're working with a positive number inside the radical. You just took the square root of the negative part. You brought it out. I, done. Now you just reduce 12. That's all you have to do. Well, 12 is 4 times 3. The I is still there. And then this square root of the 4 comes out. 2I root 3. This was more work that I want you to do, though. Could you do what I just did? Yes. But it's more work. It's one more step than I wanted you to do. Here's what I want you to do. I want you to say the square root of -4 is 2I. The 3 is stuck. Look at that. Look how much faster it is. So it's the square root of -9, 3I. -16, 4I. -25, 25I. I want you doing that. It will make your life easier. Faster work. We all like faster work. At the bell rings before I finish, I'm not concerned. You have seen enough to do all of the homework. But let's get through it. Radical on the top and bottom. That's all that means. Well, that's easy. Square root of 9, 3. Square root of -4. What's the square root of +4? 2. So what's the square root of -4? 2I, not -2, 2I. I does not equal -1. I is I. And that's all we can get through for today, but you know what? That's all you needed to do for the homework. All right, everybody. I'll see you all tomorrow.